Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to be talking about calorimetry and the specific heat equation. Okay. Now, before we jump into this video, just want to say in the previous videos that you watched, okay, we went over how to calculate enthalpy change, and we used these values that we looked up in the appendix, products minus reactants, and that gave us the enthalpy change theoretically, like by the book. Okay. What calorimetry is figuring out that enthalpy change, but it's going to be done more experimentally. Okay, so really calorimetry is just the way that we're going to measure heat flow experimentally. And the way we do that is by using the specific heat equation. Now, specific heat is the C in this equation, but let's go over all the parts of the equation. So Q is going to be the measure of heat flow, and that's in the unit joules. Mass, okay, is M, okay, and that's going to be measured in grams. And then this idea of specific heat, of which we're going to talk about in a great deal today, is measured in joules per gram degree Celsius, and then delta T is the change in temperature, and that's measured in degrees Celsius. Now, what we need to know about specific heat is that it's a quantity of energy that's required to heat up 1 gram of a substance 1 degree Celsius. So if we're talking about the specific heat of water, which is a value that you should know. As a good chemistry student, you should know the density of water, boiling point of water, freezing point of water, and now the specific heat of water. It requires 4.184 joules of energy to heat up just 1 gram of water 1 degree Celsius. So if I wanted to heat it up 2 degrees Celsius, that 1 gram, then I would need 2 chunks of 4.184. If I wanted to heat it up 3 degrees, I would need 3 chunks of 4.184 to get that temperature to rise 3 degrees. And the same thing's true about the mass. If I wanted to heat up 2 grams 1 degree Celsius, I would need 2 chunks of 4.184 joules of energy. If I had 3 grams, I would need 3 chunks of 4.184. And this ends up being a fairly high number, okay, 4.184. I know it doesn't seem like a big number, but relative to other substances, 4.184 is a pretty big number, okay? Down here, I have just kind of like a reference for you. Metals tend to have a low specific heat, typically under 1 joule per gram degree Celsius. So what does this mean? It means metals, things that conduct heat, okay, that they can heat up and cool down very quickly, okay? And that's because of their low specific heat. Where things like water that has a high specific heat of 4.184, it takes a lot more energy, over 4 times the amount, okay, to heat it up and to cool it down. So water is going to heat up very slowly, okay, and cool down very slowly relative to the metal counterpart, which is actually going to heat up quickly and cool down quickly. So let's jump into some problems. Really, today's goal is for you to get comfortable with using this Q equals MC delta T, and also being careful with kind of like the signs. And we're going to talk about that here in a few minutes. But let's get into our first example. Let's say I have this hot plate, and on top of the hot plate, I have a beaker of water, and this beaker of water contains 175 grams. This water has an initial temperature of 15 degrees Celsius. And what I'm going to do is I'm going to turn on the hot plate, okay, and some heat is good. And I'm going to use a red marker for this. Let me grab a red marker, okay, if I can find one. Sorry about that. And when I turn on the heat, okay, the heat flow is going to go from the hot plate into the beaker of water, okay? And I'm going to leave that on for a while, okay? And then in the end, the final temperature of the water is going to be 42 degrees Celsius. And what I want to figure out is how much heat entered my water system, okay? And I'm going to use this Q equals MC delta T equation to figure it out. So let's go ahead and write that down. Q equals MC delta T. What type of information do I have already? Well, I know the mass is 175 grams. The specific heat of water is 4.184. And then the last thing I need to do is figure out what the delta T is. Okay, now remember, whenever we do a change in anything, it's always going to be the final minus the initial. And this ends up being pretty important because sometimes you'll get a positive number and sometimes you'll get a negative number. Now, our temperature went from a low number to a high number. So 42 minus 15 is going to give us a change in temperature of 27 degrees Celsius. So 42 minus 15, it's actually a positive number. And that ends up being really important because all of these numbers are positive. So my Q is going to be positive. And if your Q is positive, that means that heat would be entering the system. And that's exactly what's happening here. Heat is entering the water system. So let's go ahead and get out a calculator and multiply these three numbers together. Okay, and when you do that to the nearest whole number, I get 19,769 joules of energy that are entering the water system. Now, I do want to show you that the grams cancel out, the degrees Celsius cancel out, and I'm left with this unit of joules, which is a good unit for heat energy. Okay. Now, I did really try to specify that all of these numbers are positive. So this number is positive, which means that the heat is going into the water system. Now, if I was talking about the hot plate system, if I want to know, hey, what is the heat flow? But instead of the water system, I'm talking about the hot plate system, it would be the exact same magnitude, 19,769 joules, but it would be in the negative direction because the heat flow would be leaving the hot plate system. So I always want you to be very, very careful. Whenever we're in thermodynamics, we got to be very careful with these signs. It's positive if it's entering the system, and in this first problem, this part was talking about the water system, okay? But down here, I'm talking about the hot plate system, so the heat is actually leaving that system, so that's why we have the negative sign here, okay? Let's do another one just to kind of bring that point home a little bit more closely. Kind of the same scenario, but instead of a hot plate, I'm going to use a block of ice, okay? So here's this block of ice, and I'm going to have a beaker of water on top, and the way the heat flow is going to work in this system is going to be different than the hot plate system. So if you can kind of think, hey, the heat is going to be flowing in a different direction, you're on the right, kind of like path as far as calorimetry and the specific heat equation is. But let's go ahead and set up this problem. Let's say in this problem, the beaker of water is only 125 grams this time. I have an initial temperature of 53 degrees Celsius, and I have a final temperature of 22 degrees Celsius. And I want to know the heat flow of the water system. So once again, I'm going to be focusing on the water system first, and then we'll talk about the ice system second. Now, I know they're both water, but when I say water, I mean liquid water. If I want solid water, I'll just say ice. Okay, so we're going to use our Q equals MC delta T equation. We got the mass of the water at 125. We know the specific heat of water is 4.184 joules per gram degrees Celsius. And once again, I have to come in here and figure out the change in temperature. Remember, it's always final minus initial. So 22 minus 53 is going to give us a negative number, okay? It's going to give us negative 31 degrees Celsius. And if I put a negative number in here, then when I multiply these three out, I'm going to get a negative number, okay? And it works out to be negative 16,213 joules. Now, what that means is that the heat, okay, is leaving the system. And that kind of makes sense to me because if I put a beaker of water on top of a block of ice and the beaker of water has a temperature of 53, the temperature is going to leave the beaker of water, okay, or the heat flow is going to leave the beaker of water and transfer it to the block of ice. And it'll actually start probably melting the ice, okay? So this is how you calculate heat flow. And if I wanted to talk about the ice system, okay, the Q of the ice would receive this 16,213 joules. So it would be the same magnitude, but it would be opposite in sign, because for the heat flow for the ice, the heat flow is going into the system. And if it's going into the system, that's going to be a positive number. Remember, it's only negative if it's leaving the system. So I wanted to show you that problem of how it's kind of like the reverse of the hot plate system. Okay, we got one last problem. Okay, and this one's a little bit more challenging than the other two, but it looks something like this. Let's say I have this beaker of water, and this beaker of water has 100 grams inside it. It has an initial temperature. Actually, let me do this. Okay, it has an initial temperature of 15 degrees Celsius. And what I'm going to do is I'm going to put it on a hot plate as well. And I'm going to turn on the dial and turn on the hot plate. Now, obviously, the heat flow is going to go into the water system, and it's going to leave the hot plate system. But the information that I'm going to give you is the heat flow of the hot plate system. Okay? And the heat flow of the hot plate system is going to be negative 6,802 joules. And the question that I'm going to ask you is, what is the final temperature? So I got this beaker of water with 100 grams inside it. It's at 15 degrees Celsius. I turn on the hot plate, and hot plate releases 6,802 joules of energy. Well, what I'm going to do is I'm going to use that Q to figure out, well, what is the water system heat flow? Well, if the hot plate is releasing 6,802 joules, then the water is receiving the 6,802 joules of energy. So the heat flow is going in this direction, leaving the hot plate, but entering the water system. Okay, well, if I have 3 of the 4 variables in Q equals mc delta T, then I can figure out that 4th variable. And what I have right now, because I just did this work, I have the heat flow of the water system. I have the mass of the water system. I know the specific heat of the water system, and therefore I can calculate the change in temperature. Okay? And the way I'm going to do that is by dividing by mc on both sides. So the change in temperature is actually equal to Q divided by the mass and the specific heat. The Q is a positive 6,802 joules. The mass is 100 grams. And the specific heat is 4.184 joules per gram degree Celsius. The joules are going to cancel out, the grams are going to cancel out, and I'm going to be left with degrees Celsius. So in my calculator, 6,802 joules divided by 100 divided by 4.184, that tells me that the delta T, the change in temperature, is a positive 16.3 degrees Celsius, which means that the temperature is going to increase. And if I add 16.3 degrees Celsius to 15, I'll get an answer of 31.3 degrees Celsius. So this is the introduction to calorimetry, okay, and how to use the specific heat equation, okay? And I hope you found this information useful. If you did, give it a like and subscribe, and even leaving a comment will help push this information out to other students that might be interested in learning chemistry.